So we're starting now a sequence of lessons on matrices, and you're going to see that there's a pretty abrupt shift from calculus to this topic. So we're not going to be interested that much in functions, the nuances of nonlinearity or anything like that. Matrices are about working with large systems of equations or data sets, and a lot of what understanding matrices boils down to is just figuring out what goes into what place. Uh, so let's get started. So the standard definition of a matrix is it is a rectangular array of numbers. Okay, so let's just, what does that mean? Rectangular array of numbers. What the rectangular business means is we are talking about rows and columns. That's what a matrix is. It's numbers put in rows and columns, and that's what makes it rectangular in that sense. So the typical way to write a matrix is as an uppercase letter. When it's typeset, it's almost always in boldface. I'm using boldface in the notes to let you know when I'm talking about a matrix. And so the matrix A is composed of numbers in rows and columns. And when we want to talk about those individual numbers, we index them by the row and the column. So this first number here, I'm using lowercase here, and it would be normal script, lowercase a, 1, 1. That's the number that is in the first row, first column. The next number would be the A12 element, and we would go all the way out to the A1n element. When we're talking about matrices, one of the things we're often going to be paying attention to, cultivate the habit of paying attention to, are the dimensions of the matrix. So we have m rows by n columns. And the convention is we always kind of talk about the row first. Okay, so m is the number of rows, n is the number of columns, and within the individual elements here, this is my row index, this is my column index. So let's just kind of keep going, fill in a few more elements here. My second row, I have A21. Second row, first column, A22, second row, second column. Oh, I go along, still in the second row. Now I'm in the nth column. Let's cut to the chase, down here to the last row, that would be the mth row. Here's my first column element, my second column, all the way down to my mth row, nth column. So something you'll see as we're working with matrices is that we're keeping track of a lot of stuff going on in these subscripts here, and that's just a feature of matrices. Sometimes I think people are surprised, or they view it as this irritating side thing that you're worried about subscripts when you're working with matrices. I would say the subscripts are the essence of what we're trying to do in matrices. We've got a set of numbers that have some kind of logical relationship to each other, and we're trying to organize our matrices in ways that reflect those relationships, so that, why are we putting them in matrices? So that we can work with the matrix as a whole. So we can talk about like the data set as a whole without getting bogged down in the details of every individual number that composes it. Just one other bit of lingo here. Vectors are matrices where either m equals 1 or n equals 1. We either have a single row or a single column. And guess what? We call them row vectors or column vectors. So a vector might look like vector. Again, if this was typeset, it would be boldface V, composed of number V1, V2, all the way down to Vn. When we're just working with vectors and just we're having a single index, a lot of time people just use n for everything. Anything we can do to a matrix, we can do to a vector. Okay, so all the rules that we're going to talk about for matrix algebra apply to vectors. You just think of them as matrices that are m by 1 or 1 by n. But there are things you can do to vectors that you can't do to matrices. We're not going to talk that much about them here, but that's one of the reasons why there's a distinction. Okay, so that's what a matrix is. What does it mean for a matrix to be equal to another one? It's kind of the basic thing we need to know if we're going to come up with some algebraic rules here. Well, A equals B is the same thing as saying that the ijth element of A equals the ijth element of B for all the I rows and for all the m rows. I can be any number from 1 to n, m, and j can be any number from 1 to n. So just to emphasize a point that you might be a little unsure about, if we have the matrix 1, 2, 1, negative 4, 2, 1, okay, so what is that? That is a 2-row, 3-column, 2 by 3 matrix. And we compare that to this matrix here, negative 4, 2, 2, 1, 1, also 2 by 3, and there's the same numbers here, okay? There's a negative 4 in both of them, there's 2's appearing 2 places and 1's appearing 3 places, but they're not the same thing. They're not the same thing because those numbers are appearing in different places. So the point here is that the position of those numbers matters. Again, if you find yourself being irritated about how much is going on in those fiddly little subscripts, that's why. It's because it matters what number is in what place. So what can we do to matrices? One thing we can do is we can take a transpose of a matrix. Okay, when we take a transpose, what we're doing is just switching the rows and columns. Okay, so we have matrix A, where we're thinking about generic element being Aij. For A prime, the generic element is Aji. We've switched the rows and the columns here. So let's take a specific A, the one we were looking at just a minute ago, 2, 2, 1, 1. So if I start with A, I go to A prime by making the rows of A the columns of A prime. So my first row of A, 1, 2, 1, that is my first column of A prime. And my second row of A is my second column of A prime. So negative 4, 2, 1. Okay, so a couple of comments. When you take the transpose of a matrix that isn't square, you're going to get a matrix that has a different shape. That's just a fact, and be aware of that. Another thing to notice is that the transpose of the transpose, let's do that here. Look at our A prime and take its transpose. That's going to get us back to the original matrix. And let me just make my prime look a little bit clearer here. Taking the transpose of this guy. My first row here is my first column, maybe 4, and 1, 2, 2, 1, 1. I get back to where I started there. Transpose is its own inverse. Another thing about transpose is sometimes you might see this alternative notation. Sometimes we write it with a subscript T. Okay, I used to using the primes, but you'll certainly see the T sometimes in books. All right. Another thing just to observe about transposes is if you take the transpose of a square matrix, you don't change the dimension, okay, but you do change the matrix, okay? So B, 3, -1, 4, 2, 0, 0, 0, 2. Switching the rows and columns, taking the transpose here gives us 3, 2, 0, -1, 0, 5, 4, 0, 2. The B does not equal B prime unless we start off with a symmetric matrix. And symmetric is just what you think it would be. In fact, the definition of symmetric is that it's its own transpose, but what that looks like would be something like matrix C here, 3, 2, 1, 2, 5, 0, 1, 0, 1. If we look at that, this matrix is symmetric, and the axis of symmetry is this main diagonal here, the diagonal that starts up here in the northwest and goes down to the southeast. And on either side of that, we've got the 2, 1 element being the same as the 1, 2, the 3, 1 element being the same as the 1, 3, the 2, 3 element being the same, sorry, the 3, 2 element being the same as the 2, 3 here. Okay, so symmetric means that the matrix is equal to its own transpose, and sometimes knowing that can be helpful. Certainly if we're trying to calculate a matrix and we know it's symmetric, it's pretty cool to know that we only have to calculate half of the numbers. Yeah. Right. So transpose is one operation we can perform on matrices. Let's talk about 2 more. Okay, so the first one is scalar addition. So a scalar is just a number, and it's a word that gets used in the context of vectors and matrices. So it's kind of emphasizing the fact that it's a number that's interacting with these things that are composed of numbers but are bigger things. In this case, like a matrix. Okay, so if we have matrix A and we want to multiply it by scalar number alpha, all we do is multiply every element of A by that scalar. So we're just multiplying each element in A. Okay, so if we start off with A equals 1, 2, 0, -1, and we want to multiply that by scalar, -2, -2a is equal to -2, -4, 0, +2. So I just went through and multiplied every element of that matrix by the scalar. Really nothing remotely complicated here. And another process we can do with matrices that's also pretty intuitive and straightforward is addition. We can add matrices. So if we add matrix A and B to get matrix C, guess what we do? We add up the corresponding elements of A and B here. So we get that by finding Cij as the sum of Aij plus Bij. Okay, so if we have 1, -2, 0, 0 plus the plus there, 1, 1, 1, 1 there. This is my A, this is my B. To get my C, I'm just gonna add the 1, 1 terms of each. That gives me a 2. the 1, 2 terms. So A12 plus B12, that's -2 plus 1, sounds like -1. 0 plus 1 is 1, and 1 there. So again, totally straightforward, except for one little thing. There is this issue. You have to have matrices that are the same dimension in order to do this. In order to have, say, a B12 to add to A12, you have to have an element in those positions in each of the matrices. So that's the first example we're going to see of a conformability requirement. What does that mean? A and B are conformable for addition only if they have the same number of rows and the same number of columns. Okay. So if we had that same A matrix, 1, -2, 0, 0, and we want to add 1, 3, 1, this 3 by 1 column vector, sorry, that's not going to happen. Okay, so this is not defined. These matrices are not conformable. Okay, both of them have a 1, 2 and a 2, 1 element, but there's no 1, 2 element to add to the -2, and there's no 3, 1 element over here to add to the 1. So you can't even do this addition. And this is something we're going to see is a concern going forward with matrix algebra, that we can't always perform operations on any two matrices. We have to think about their shapes and whether they're conformable. We didn't have to worry about that when we talked about transpose or scalar multiplication. No conformability restrictions there. You can take the transpose of any matrix you want, and you can multiply any matrix you want by any scalar you want. Addition, the conformability requirements are pretty straightforward, that the two matrices have to have the same number of rows and the same number of columns. Another way to just think about that is the two matrices have to have the same shape. Things get a little bit trickier when we move to matrix multiplication. And so we're going to make that its own lesson, and I'll see you in that one.